For decades, a mathematical conjecture called the Fishbone Conjecture has resisted all attempts to prove it. And now we know why. The conjecture has been shown to be false in a new paper by Lawrence Hallam, who's come up with a pretty interesting counterexample. My interview with Lawrence is at the end of the video, but let's begin by trying to understand what is this conjecture all about. If I consider a bunch of numbers, 1, 2, 3, 4, 5, they have something called an ordering on them. Like, we would all be happy saying that 2 is less than 3 and 3 is less than 4 and so forth. But in many mathematical structures, we don't have what's called a total order. We have something called a partial order instead. For example, imagine you've got these points A, B, C, D, E, F, and G, but they're sort of arranged on this interesting roadway. If you look at 2 points like B and C, they're on a road, C is more to the right of B, and we might say in this case that C is greater than B. But if I instead look at, for example, C and E, they're on different roads, they're incomparable. Here I'm using this perpendicular symbol to indicate that they're just incomparable. It's not that C is less than E or that E is less than C, there's just no way to compare them. I mean, even if you go to something like C and G, the fact that G is further to the right is irrelevant. They're on different pathways, they're incomparable. And so we will call this a poset for partially ordered set. And structures like this come up all over the place in mathematics. Okay, 2 other pieces of terminology. The first is the idea of a chain. So a chain is something like A, B, C, D. These are 4 points all in a row, all along the same roadway, to use my metaphor here. In other words, you take any 2 of them and they're comparable in this partially ordered set. Another example would be A, B, C, F. That's a different chain. And you don't actually have to have all of the middle points. Like a simple chain would just be A and C, sort of skipping B. A and C are 2 points on one of those roadways, so they're comparable, so that would be considered a chain as well. In contrast, we might consider something called an antichain, where with a chain, every pair of points was comparable, and an antichain, every pair of points is incomparable. So an example of an antichain would be C and E. They are incomparable, that makes an antichain. Another one would be something like E, F, D. No 2 of those 3 points are comparable, so it forms an antichain. Okay, so the example I've given you so far is this sort of pictorial example. Let's try to come up with a very concrete example. I want you to imagine the natural numbers cross with the natural numbers. So this is kind of like 2-dimensional space, but I'm only considering pairs where the coordinates are both natural numbers. So this is a set. And now I'm going to give this set the structure of a partially ordered set by telling you what the order is. So if you take 2 points, x1, y1, and x2, y2, so we'll say one pair is less than the other pair if the x-coordinates are smaller in the normal sense of ordering, the normal way you would just order the numbers, and then also for the y-coordinates. So the x1 has to be less than or equal to the x2, and the y1 has to be less than or equal to the y2. To make this more precise, let me put up a specific example like 3, 2. So that is a specific point. What are all of the points that are smaller than this in this particular ordering? Well, it's all points whose x-coordinates are smaller than or equal to 3, and whose y-coordinates are smaller than or equal to 2. In other words, it's all of these ones that I've highlighted. This, by the way, is called the Cartesian ordering. So here's my set. I have an order on it. And now let's consider what some chains and antichains are. So here's an example of a chain. Any 2 points along that chain has the property that the 1 point is less than the other point. 0, 0 is less than 1, 0, which is less than 2, 1, which is less than 2, 2, which is less than 3, 2. That is a chain in this particular ordering. But it's a partial ordering because not every pair is comparable. For example, consider 2, 3, and 3, 2. If a point is to be smaller than another, both the x-coordinates and the y-coordinates have to be smaller. But here for 2, 3, the x-coordinate is smaller than 3, 2, but the y is not. So these 2 points are incomparable, and thus an antichain would be listing these 2 particular points. They are not comparable. Okay, so hopefully we've got the idea of a partially ordered set, chains in partially ordered sets, and antichains in partially ordered sets. The next thing I want to tell you about is a fishbone. Okay, so that's a picture of a fish skeleton. Ignore the head and the tail for a moment. And I kind of want to imagine it more of a graph theoretic sense as looking something like this. There's a central spine, and then all of the other points get connected to that central spine. In a moment, our central spine will be a chain, and then all the sort of ribs are going to be antichains. So very loosely, a graph that looks like this, maybe we'll call it a fishbone graph. Okay, so back to my original example here. Do I have what's called a fishbone? So our definition here is that we have a partition of all of these points have to either belong on chains or antichains. The chain is like the spine of our fish, so all of the other points need to get connected down to the spine. And the other points get connected along antichains that are disjoint, which means they don't overlap. The two different ribs of the fish don't intersect. They only intersect the spine. Okay, so let's see if we can find a fishbone-like structure in this graph. There's many. You can pause and see if you can find a couple. But here's one. Let's take as the spine ABCD. That's a chain. And then I have three remaining points to put somewhere, the E, the F, and the G. They have to go on antichains. So I have one antichain, which is the antichain E to C. That connects the point E into C along an antichain. And then I also have the antichain GFD that connects G and F into the main spine along the antichain GFD. So every point is covered. We've done our partition. It's got a spine, that's the pink chain. And then it has the various ribs. These are the antichains that connect the other points down to the chain. Okay, so this example has a fishbone. Do all partially ordered sets have fishbones? Well, let's investigate. Actually, let's go back to our old example here with the natural numbers cross the natural numbers with this ordering that we've listed. So I need to find a spine and then I need to find all the ribs. Well, one example of a spine would be just going up the y-axis here. 0, 0 is less than 0, 1, which is less than 0, 2, which is less than 0, 3. That's a chain. And then to make a fishbone, I would need to take all the other points and connect it down to this spot. Well, how about something like this? I'll take the point 1, 0, and I'll connect it up to 0, 1. That's an antichain, right? 1, 0, and 0, 1 aren't comparable. And then I have 2, 0, and 1, 1, and 0, 2. Again, that's another antichain. And I can keep on going all the way along. And if I kept doing this, every single point here would get connected to the spine. So I found a weird fishbone. It's kind of an infinite fishbone, right? The spine is infinitely long, has infinitely many ribs, but it's a fishbone in this structure. Let's note just in passing that if I look at the antichains I've come up with, even though they can get arbitrarily large, right? Like the x-axis is infinite. I could start at, a million zero, a billion zero, a trillion zero. Any specific antichain that you choose actually is finite. If I start at a billion zero, then it goes up in that diagonal and connects to 0, a billion. And it actually turns out there's no infinite antichains here. There's antichains of arbitrary length, but no infinite ones. So it's starting to look like all of these partially ordered sets have fishbones, right? Well, let's see another example. Okay. This is almost the same. I've made two changes. The first is I've cut out half of the points. So I'm only going to consider the points in the natural numbers, cross the natural numbers, beneath that main diagonal. So my underlying set has sort of been cut in half. And then I'm also going to change the ordering. Remember previously the ordering was the x1 had to be less than the x2 and the y1 had to be less than the y2. I'm going to be more demanding. I'm going to say that the x1 has to be equal to x2. In order to be compared, you have to have the same x coordinate. So here is a chain in this particular system. That chain can't go to the left or right. It has to have the same x coordinates. So it can only go straight up. And then here's an example of a potential antichain. All that really matters is that I don't ever go straight up with the same x coordinate. Can I make a fishbone in this particular structure? I could have started at 4, 0 or 5, 0 or a billion 0, but no matter where I start, my chain is definitely finite. But if I want to make a fishbone, and I want to take all the other points and connect them via antichains to this, well, I have infinitely many points to connect to this finite spine. I'm going to have a problem. So let me try and do one way I might try to come up with some antichains, something like this. I'll take my antichains just to be keeping on going horizontal. Those are always antichains. That's fine. But I can only connect 4 antichains to it if they're going to be disjoint. So then if I take some point higher than whatever the highest antichain that I've got here, how would I ever connect that point down? If it was to connect down to the chain, then there would be an intersection of the chains. They would no longer be disjoint. I wouldn't get a fishbone. So this different partially ordered set, different ordering, it doesn't have a fishbone. So what's the problem here? Well, One of the things that are worth noting in this example is that while I don't have a fishbone, I actually have an infinite antichain. Like imagine I just went along horizontally forever. These are the natural numbers, they go on forever. So this is an antichain and it's an infinite one, a little different than the example we'd seen before. Okay, so we've seen examples with a fishbone and with an infinite antichain. So the conjecture, the Aharoni and Korman conjecture of 1992, was that every single post set, every single partially ordered set, has one of those two things. Either it has an infinite antichain or it has a fishbone. So now in the story, we need to turn to Lawrence Hallam, who is a PhD student at Cambridge, who was very generous to be able to speak to us on our channel here. And let's see how he describes his new paper.
The purpose of the paper is sort of to try and like resolve the conjecture as like thoroughly as possible. So it shows the conjecture is false. It could, like, we can construct a post set which doesn't have a fishbone, where sort of you can like build this sort of intricate structure where it's impossible to find this. But that's sort of sometimes a bit of a disappointment to have a paper that only says that, just says, oh, it's false.
Right.
So I've also tried to actually the vast majority of the page count of the paper is saying, okay, it's false. Here's this big counterexample, but also like the counterexample is pretty big. It's got a lot of structure, and the rest of the paper is sort of saying like, there's a reason why the counterexample has to be so big and have so much structure, because there's this. For a lot of post sets, the conjecture is true, and there's a reason why it took a long time for anyone to find a counterexample, because for a lot of post sets and a lot of like any example you might try and write down of a post set, the conjecture does hold true. So it sort of is trying to do this, in both directions.
Did you go into it thinking that this was likely false and that you were likely to come up with a counterexample? Did you expect that, or did you think, oh no, I actually am more interested in figuring out when is a version of the conjecture with added conditions true? Like, what was your spot coming in?
Yeah, so I think for a while I was like trying. Well, I think basically I flip-flopped a lot of times on it. I was working on it for quite a few months, and then there was a while I was like, yeah, I've got these ideas. I can put these together and make a proof. That'll work. And then a bit later, oh, it doesn't quite work for this, but I can build this post set, and that's going to be a counterexample. And then the counterexample fell apart. So it's like, oh, but I can fix that and prove it. And went backwards and forwards a few times. And then the final draft was like, I think even only a few weeks before I put it online, I was sort of thought it was a complete proof until like, oh, I found this small problem. And then from that, like, well, the first time I like wrote down the counterexample, like, great, there's a counterexample. And then like sat down to actually prove the counterexample was a counterexample. And then partway through that, realized that actually the conjecture was still true for the counterexample. And there was a while where I was like, it looks so much like a counterexample, but the conjecture's still true. It's like this one thing stopping it being for a counterexample is like the conjecture's true. But it really felt like it was sort of, kind of morally was a counterexample, and I just needed to like change things a bit. And then sure enough, I did find a way of like changing it and moving things around a bit to produce an actual counterexample. So I think like the counterexample was pretty much the last thing I proved while working on this at all.
Right, so you'd prove the refined theorem first. That
Yeah.
if you don't have these bad intervals, then it's true. And then it was only then where you were looking in that set of examples to see if you could find the counterexample right at the end.
Yeah. And there was a while where after like my first attempt at making a counterexample failed, there was a while where I thought, oh, I'm actually just going to have to put up a paper saying I can kind of prove it a bit, but not all the time. So I've had a few goes at making this counterexample, and they just kept not working. So yeah, it took quite a few goes to actually like get all the pieces to fit together in the right way. Yeah,
I love that. Feels very much like how math research often is as you're played around in it. Yeah. It's funny, I don't know if you saw, but Timothy Gowers had this kind of hilarious tweet about it. And one of the things he said was that his spies had told him that quite a number of people perhaps had been working away on the conjecture. What's your sense of it, of how challenging has it been in the last 30 years or whatever since it was conjectured?
Yeah, so I think I was a little bit surprised when I heard that like Tim Gowers had tweeted about it, and I had a couple of emails from other like professors in the department I'm in saying like, oh wow, you've solved this, that's incredible and something. And I was a bit surprised because like if you go and look at the actual papers that have been written about this, there's not that many. There are some saying, oh, I can prove this small case, and I can prove this, and I can prove that. But there really isn't that much. So I sort of didn't realize the extent to which people had worked on this, because I think a lot of people had worked on it and tried to prove it was true and basically made no progress. And at the end of that, like hadn't written anything down about it. So it's sort of only like now I've been finding out that like, oh, actually lots of people had worked on this, but then they sort of what all they've done is I tried to prove it for a while and couldn't prove it, and then that never got written down anywhere. So actually, I'm only sort of finding out about that now.
Yeah, I sometimes think in math research that we do ourselves a disservice of not putting out our failed attempts at disproving things, because it can have exactly the scenario you're talking about, where a bunch of people might have been spinning their tires at something that ultimately just wasn't true, but we don't necessarily hear about all those failed attempts.
Yeah, absolutely. Yeah, and I'm sure I've probably wasted some time like trying things that other people have tried many times before, and like it's definitely something I think in maths and probably in science in general as well that people need to get better at, and there sort of isn't really the system in place at the moment to figure out how to share this like I tried this and it didn't work type result.
So you've now been involved in a couple of disproving of conjectures. So like I done this previous video on the bunk bed conjecture. And you very briefly showed up there because you had been considering possible generalizations to the bunk bed conjecture, seeing whether those were true, and then disproving them. And it turned out that your disproof of one of the generalizations into hypergraphs was the key piece, really, that was then proved the original, or disproved rather the original bunk bed conjecture. But I saw you, and I was looking down your Google Scholar, you've done other conjectures that disprove. So there's something about conjectures and disproving them that particularly draws you, or is it just sort of coincidence that you just happen to have a couple nice disproofs?
I think it is something I've like kind of deliberately tried to work on to an extent. So certainly for the bunk bed conjecture and a couple of the other like more minor things I worked on, not so much with this one. I ended up like discovering counterexamples because I think it's a bit of a something that happens quite a bit in some of these areas is people make conjectures, but then like don't test them that thoroughly. And so I also partially come from a bit of a coding background. So it's quite an easy thing to do, like look at a conjecture, think, I can just write some code to test some small cases, see if it's true or not. And I think sort of, especially now having like worked on this and worked on the bunk bed conjecture, I think it is probably, in general, I think there probably are a lot of things out there that feel like they should be true, or like intuitively true, but then we can't prove them. And I feel like a lot of the cases, a lot of the times, that might be because they're actually false. That's like why we can't prove them. Yeah, and so I have sort of like been looking for these problems at a bit as like an angle where I think there is like work to be done.
Yeah, and it's really interesting because somehow, there's a lot of glory in proving a big theorem, right? Someone's made this conjecture, it's held for decades, and finally you get to prove it. But there's also something in saying, no, that conjecture never was correct. Actually, I've got this crazy, very large, very bizarre counterexample to it. There's also a real beauty in that, at least in my opinion.
Yeah, no, I think, yeah, I mean, I certainly think so. I think there still is definitely a perception that there's more glory in proving things. I know sort of when I've spoken to like my supervisor and other people sort of in the area, they've sort of said things like, "Oh, this is cool," but like, "Oh, it would have been so much more cool if there was a proof." That then, like, I feel like there is a bit of a sense that like a proof is like advancing knowledge, and a counterexample is more saying, "Oh no, there wasn't anything here." But I think you are right that like there is like so when you find a counterexample, especially to a conjecture that people have believed, it really is telling us like people believe this was true and it's not true. So there's been something like wrong with our intuition about the problem. We really are like discovering we were thinking about this problem in an incorrect way, in some way.
What I really liked about Lauren's paper is he didn't just find a counterexample, is he said that if your post set is nice in a certain way, then the conjecture actually is true when you add in this additional niceness condition. So he has a theorem in his paper that's very analogous to the original conjecture, but it's now a theorem. And it says that a post set that's countable and vacillating without an infinite antichain is going to have a fishbone. So he's added two things here. First of all, it needs to be at most countably infinite. But the more interesting one is this new word of vacillating. Okay, so I put up the technical statement about what this extra nice condition that he wants to have called vacillating is. You can go to the paper to read more of the details. But now let me share you what he said about the intuition behind this idea. So are you able to give a little intuition about what's going, like you're talking about, you have the sort of these infinite intervals that themselves can be broken up as a whole bunch of infinite intervals.
Yeah.
Are you able to share a little bit of the intuition about why that is problematic, or does that get a little too technical?
I think I can say a bit about it. I think so. So there's a few cases of the conjecture that are true and very easy to prove. So if the post set is finite, it's very easy because we can sort of like basically, as soon as you write it down, you can see it just like naturally splits into levels, and these are like the levels we want to use.
Yeah.
And an extension of this would be to a pose set called well-founded, when it sort of is now infinite, but there's still, in a sense, a way of splitting it up into levels. And that was infinitely many levels, but it does like nice, naturally, immediately split up into levels. And when it does this, the conjecture is true. So a case where this doesn't happen is sort of what we need to look. We need to look at something that's like really like not well-founded at all. And another thing the conjecture that helps the conjecture being true is if you can like split your pose set up into chunks, which like really like divide up quite nicely, then you can sort of say, well, if I can prove it on each chunk, then maybe I can like stitch everything together between the chunks.
Right.
And so if you could cut the pose set up into chunks, each of which was well-founded or like well-founded the other way up, called co-well-founded, if you could like chop it up into nice sections like this, then the conjecture would be true. And this condition called like vacillating or not vacillating is the problem case. Is basically exactly saying you've got this chunk of the pose set that is like not at all well-founded. You've got sort of so well-founded in a sense means like increasing sequences which like start somewhere and tend up to infinity, and you can also have the opposite that works just as well. You start somewhere and tend down to infinity.
Right, that's the co-well-founded, I guess.
Yeah, the co-well-founded ones. Yeah, and the problem case is basically when you have something that like mixes the two together. So you have sort of an infinite increasing sequence, and then you have like an infinite decreasing sequence of these infinite increasing sequences. So it's like the real like mixing together of the two. That's like the intuition from either. Yeah. I think the only other thing I'd say is that it's something that's true with this problem when we're working with infinite structures and lots of other ones. Is that we working here in what's called like countable infinities, which in some way are like the smallest and simplest infinite structures, and there's still infinite structures beyond that, and in those cases like everything gets way more complicated. And yeah, asking any of these questions about any of these bigger infinite structures, then there's like all kinds of new problems and things to run into there.
Right,
Yeah.
and I even saw you, I think you had a quote where you're sort of like, you sort of suspect that some analogs, you can stay here, but as soon as you leave the countable infinity, things are just maybe technically challenging.
Yeah, I sort of had like some...
Still...
Yeah, like I think maybe still true, but then this is also something like I'm not like an expert in these larger infinities. There's people who know way more about it than me. And so I was like, I had some like sketch proofs written down, like maybe I can sort of make this work into bigger infinities, but then there's like so much going, so many like so many problems you can run into there. In the end, I was like, I'm not gonna sort of. I feel like if I try and write this down, it'll just definitely be wrong. So I'll just like, leave it for someone who knows more about that stuff than me to deal with.
A massive thank you to Lawrence for coming on this channel. Please do check out a link to his paper down below. Do note that this is a preprint, which means it has not yet been peer-reviewed and published in a journal. But nevertheless, I thought the story was so cool that I really wanted to share it with all of you. If you have any thoughts or questions, leave them down in the comments below. We'll do some more math in the next video.